Okay, hello to this video. So in this video we are going to use the law of Biot-Savart to calculate the magnetic field around wires. We are going to start out with this infinitely long wire here and use the law of Biot-Savart to calculate the magnetic field around it. And particularly the law of Biot-Savart is interesting because you can also have these finite length wires here, and for such a wire piece you can calculate the magnetic field around it. This is not possible with the Ampere's circuital law, which is only usable if you have a highly symmetric situation. So for the infinitely long wire, straight, long, infinitely long wire, there you can use the Ampere's circuital law because it's completely symmetric. So no beginning, no end, the free space around it, so everything is symmetric. As soon as you have a finite piece of wire, it's the Ampere circuital law is only an approximation for the situation because you have the ends here also. So the question is, how large is the magnetic field at some position from the wire if you only have this finite piece of wire and not an infinitely long wire? And this I'm going to show you how to calculate it with the law of Biot-Savart. Okay, so the geometry is as follows. So we will assume we have a wire that is infinitely long first of all, and afterwards we will go to the finite length wire. So for now we just assume it is extending infinitely long. We have a current that is flowing through from bottom to top. We are in magnetostatics here. That means we have a current that is not changing in time. So we have always the same constant current I. And then the magnetic field around the wire is given by the right-hand rule. So the wire here is surrounded by the magnetic field like this. Okay, if I draw this here, it means the lines are around this. So this is the magnetic field B. We often show B in our diagrams instead of the magnetic field strength H. So H is the magnetic field. Actually, B is the magnetic flux density. We are going to calculate the magnetic field here, but as is typical, I'm showing the magnetic flux density. Okay, so the question we have is then, if we have a point P at a certain distance, let's say P is here, what is the magnetic field at this point P at location R in relation to the wire? And let's assume that this distance here, if we take at a normal angle the distance, that this distance is given by A to this point P, and we want to calculate the field strength. So first of all, we are going to do it with the law of Biot-Savart. So let's write down the Biot-Savart law. This is given by the magnetic field strength H at a position R is equal to I over 4 pi, so the current that is causing the field. And then we have to integrate over the wire line L, dl cross ER divided, so this unit vector in R direction divided by R squared. And this radius R here that I'm talking about, that is the element or the vector that is connecting the element of the integration dl with the point P. So we have this vector here. This is our vector R. And this vector R connecting the line element of the integration with the point P then has a length given by capital R and a direction given by a unit vector E in direction of R. So this is how we write it. And so this ER here is a unit vector of length 1 in the direction of the vector R. And what we want to do now is we want to use this law of Biot-Savart here in order to calculate the magnetic field strength. Okay, so first of all, we will just calculate the absolute value of H. So let's first of all go to the absolute value of H at the position R. And this absolute value is then I over 4 pi. And we integrate over the absolute value of this cross product. And I'm going here to write it as vector R over R to the third. So I have put in that the vector ER, the unit vector, is given by the total vector R divided by the length of the total vector R. And so R, since it's a length, it's a positive value, and we have to take the absolute value of the cross product. Okay, so we want to calculate this cross product here, and we do this by taking the right finger rule for dl cross this vector R. And so to do that, we take the thumb in dl direction, the index finger in R direction, and then the middle finger points to the direction the field is showing. And in this case, then that means the field is showing, as we also see it here, out of the plane that is formed by this triangle here. It's pointing out of the plane, the B field in this point P here. Okay, so if we calculate this, then it means we have to take the sign of that is between the element dl and R. So we have here this is the sign alpha, and our integral is then given by I over 4 pi, integral over the length of the wire L, and this is then the length of the element dl times the length of the element R times the sine of the angle between the two, and divided over R to the third power. And this is the absolute value here. And this integral needs to be solved. So the problem with solving this integral is that in this integral here, the length of R depends on the position we are at here. So if we are getting closer to this point here, then the distance is getting less and less, while if we are going far away, so we're down here, for example, then the R gets longer and longer. So the length of R depends on the position of our integration. Also, the angle alpha we have here, it also depends on the position of our integration. If we're at this point here, the angle alpha is 90 degrees. If we are going to minus infinity for an infinitely long fiber, then the angle alpha is going towards 0. If we are going up all the way, then the angle alpha is going towards 180 degrees. So if we are just a bit above this here, then the angle alpha is going to be, for example, larger. So if we're at this point here, let's say, we're considering this element dl, then this would be the connection vector R, and this would be the angle alpha dash. It would it would be larger than 90 degrees, and this depends also on the position. So that means that both the R and the alpha are not constants, but they depend on the position of what we are integrating at the moment. Also, for the infinitely long fiber, we are going to integrate here the length from minus infinity to infinity, while then for the finite piece of fiber afterwards, we are going to consider only part of the length. Okay, so first of all, we are going to go for the infinitely long fiber, so infinitely long wire. So that means we integrate from minus infinity to infinity. And so let's just put this down here. So we integrate from minus infinity to infinity. And now, in order to do the integration, we have to bring all the variables or we have to formulate all the variables as a function of one single variable. And it has been seen in the past that actually to solve this integral here, it's easiest to formulate everything in terms of the angle alpha instead of the position L. So we are not doing the position L from minus infinity to infinity, but we are considering the angle alpha from 0 degrees to 180 degrees. So I'm going to transform this integral to I over 4 pi, 0 degrees to 180 degrees, and we are going to integrate over alpha. And now, okay, sine alpha, that is already an alpha. We have to write r and also then the dl as a function of alpha. So let's consider, first of all, how large the r is for different alpha values. And so for this r, we get, we have the equation that the sine of alpha is the same as a divided by r, so a divided by r. So that means if we want to formulate the r as a function of alpha, r is then equal to a over sine alpha. Okay, so that we already know we can plug in now for the r. Then we need to have the connection between the dl and the alpha. And to do this, we can actually use a little trick, you could say, and that is we consider here this element that is part of the arc of a circle that we put around the point P, and that has so the total circle would be like this, going all the way around. And it has the radius r, and then this is an element d alpha of the circle. So this d alpha is this element up here. And this element d alpha is connected to the part down here by that it's a part of the circle. So we have r times d alpha is this little piece here. And also this can be then put in connection to the dl by considering that the dl and this part of the circle here are connected by a dl times sine alpha. So if we just approximately, if we say it's a very small, infinitesimal small piece dl, it means that the straight length dl has the same length as the circular arc element for very small parts. And that is why we can use this second equation. So now we can then write the dl also as a function of alpha, and we can put in this r from before, and therefore we obtain here in plugging both of these equations in. So if we plug in this equation here and this equation there into the integral, we finally are left with sine alpha over a d alpha. And the a is now a constant, can be pulled in front, and so it means we only have to integrate over the sine alpha. So this integration, I over 4 pi a, integral minus cosine alpha from 0 to 180 degrees. And if we plug this in, so we have for 180 degrees, the cosine of alpha is -1, so we have minus 1 plus 1 minus cosine of 0 degrees, so a total of the integral is 2. So this is equal to I over 2 pi a. And this is actually exactly the same, of course, as we obtain from Ampere's circuital law for an infinitely long wire. The advantage of doing this whole calculation is that now, with very little change, we can go to the finite length wire that I have here. And what we need to change only if we go to the finite length wire is in this part of the integral, is in this part of the integral. So here I plugged in that we integrate from minus infinity to infinity. So if we now consider a finite piece of wire, so if we have a wire that only extends from here to here, let's say, so our point P is now at this location here. This is our point P of R. And we only consider this small part of wire and want to calculate what field does it cause. It means we only need to integrate then from this location to this location. So we don't need to integrate or this angle to this angle then, location DL down here to the element up here. Or regarding the angle, it means we calculate from this angle alpha 1 to this angle alpha 2 here. And then all that we have to change is this at this point here, the integral. So we have h of r, the absolute value of h of r is then equal to I over 4 pi integral, instead of from 0 degrees to 100 degrees, from alpha 1 to alpha 2 sine alpha over a d alpha. So that is the whole change we need to do if we don't have an infinitely long but a finite piece of wire. And if we plug this then in, or if we solve this integral here, it means we get the h of r is equal to I over 2 pi a, absolute value of cosine of alpha 1 minus cosine of alpha 2. And this is our result for the finite piece of wire. And you might ask now that for the finite piece of wire, well, I mean, it has to be connected somehow. We cannot just have this piece of wire without any connection. How will it carry a current I if there's no connection? Of course, that is completely correct. You do need connections. So you could have this piece of wire, and then there could be a different piece of wire going somewhere connecting to this wire. The point now is, if you are in free space, remember, you can use the superposition principle. So if you know how to calculate one piece of wire for this small piece, then you can also connect this piece of wire to another piece of wire, basically. So you have some next wire going on here. And the superposition principle tells you that you can calculate the magnetic field caused by the one piece of wire and add it to the result of the magnetic field caused by the second piece of wire. And the total field is just the sum of the two, as long as you are in a linear situation, that is, you don't have any nonlinear effects. So if we are in free space, in vacuum, then we don't have nonlinear effects, and we can just add the two fields with the superposition principle. So it might seem trivial that you have this one small piece of wire, and now you can calculate the magnetic field. But think of all the printed circuit boards, of all the different circuits you have, and with this piece of information that you can calculate the magnetic field at an arbitrary point around an arbitrary length piece of wire, you can, by superposition principle, calculate all the other situations. Of course, we do have a bit of a problem in magnetic materials if we are going towards materials with hysteresis effects, nonlinear HB relations. Then we have to see how the superposition principle holds. But this is not the topic today. Today we just looked at this one piece of wire. Thanks for watching.